How do modern assembly technologies and mega-heavy transport systems move colossal structures across continents with breathtaking precision and power today? The Upcast SG tube technology, developed by Upcast, represents a modern upward continuous casting solution that significantly shortens the traditional copper tube production process. This advanced method is primarily used to manufacture high-quality, oxygen-free copper and copper alloy wire rods and tubes, offering exceptional electrical conductivity and excellent drawability. At the core of the system is the upward casting principle. In this process, molten copper is held in a controlled furnace environment and vertically drawn upward through a graphite mold and a precisely engineered cooler. As the molten metal rises, it solidifies into a rod or tube form. Because the metal is drawn upward rather than poured downward, its exposure to air is minimized. This controlled atmosphere effectively prevents oxygen contamination, ensuring the production of oxygen-free copper with superior purity. The result is a finished tube or rod with consistent grain structure, high surface quality, and excellent mechanical properties. One of the key advantages of the Upcast SG tube technology is its modular and flexible design. The system can be configured with either single or double furnaces, depending on production requirements. In addition, it supports multi-strand casting, allowing manufacturers to produce multiple rods or tubes simultaneously. Different diameters can be cast at the same time, which increases productivity and enables efficient adaptation to varying customer demands. This flexibility makes the technology suitable for both medium-scale and large-scale production facilities. Beyond pure copper, the system also demonstrates strong material versatility. While it is optimized for oxygen-free copper, it can process a wide range of copper alloys, including brasses and bronzes. It is also capable of casting specialty alloys, such as copper magnesium, which are widely used in automotive and railway applications due to their combination of strength and electrical performance. This adaptability broadens the range of industries that can benefit from the process. Efficiency is another major advantage. Recent technical upgrades, particularly in cooler design, have increased casting speeds by up to 25%. At the same time, energy consumption has been reduced by approximately 10%. These improvements not only enhance productivity, but also lower operational costs and environmental impact. The entire process is highly automated through advanced PLC control systems and servo motor drives. Automation ensures precise temperature control, stable casting speed, and consistent product quality. It also reduces manual labor requirements, making the system user-friendly and reliable. Overall, The Upcast SG tube upward continuous casting technology provides a streamlined, efficient, and high-quality solution that shortens the copper tube production chain while delivering superior material performance. The process begins with the preparation of the casting mold for the pump impeller. An impeller core is first manufactured to form the internal passages and hollow sections of the component. This core is carefully positioned to ensure it will accurately create the internal geometry of the blades and hub. At the filling station, multi-part molding boxes arrive and are prepared to receive the pattern and molding material. The impeller pattern, which represents the exact external shape of the final product, is placed inside the molding box together with the core. A carefully prepared mixture of sand and clay is then added into the molding box. This mixture must have the proper consistency and moisture content to guarantee strength and precision. The sand is packed tightly around the pattern and the core to capture every contour of the blade, edges, hub, and vanes. Once the molding box is completely filled, it is flipped over. This step allows the operators to separate the sections of the mold and remove the pattern. After removal, the compressed sand clearly shows the impeller core cavities, forming a precise negative impression of both the internal and external features. For certain models, such as the jet thruster JT90 impeller pattern, several patterns may be arranged in one molding box to optimize production. Horizontal runners can be seen between the patterns. These channels will distribute molten metal evenly during pouring. After inspection, the parts of the molding box are joined together again to form a complete closed mold. Proper alignment of the impeller pattern and core cavities is carefully checked to prevent dimensional errors. The finished two-part molding boxes are then clamped securely, ensuring they will withstand the pressure and temperature of the molten metal. Meanwhile, the metal preparation process begins. An induction furnace is lowered onto a melting pot, containing the raw materials for the aluminum-bronze alloy. The composition of the alloy is adjusted strictly according to technical specifications. The correct proportion of aluminum, copper, and other elements is essential to achieve the required strength, corrosion resistance, and wear resistance of the final impeller. As the alloy melts, a temperature probe is inserted into the molten metal to continuously monitor heat levels. Maintaining the correct temperature ensures optimal fluidity and reduces the risk of shrinkage or incomplete filling. During melting, impurities rise to the surface in the form of slag. These impurities are carefully removed to improve the purity and structural integrity of the casting. When the molten aluminum bronze reaches the specified temperature and composition, it is ready for pouring. The liquid metal is transferred and poured into the gating system of the prepared molds. The gating system includes sprues, runners, and entry points designed to guide the metal smoothly into each cavity. The horizontal runners distribute the molten alloy evenly to all impeller shapes within the mold, minimizing turbulence and preventing air entrapment. The molds are left undisturbed while the metal cools and solidifies. Controlled cooling is critical to prevent internal stresses, cracks, or deformation. As the metal transitions from liquid to solid, it takes on the exact shape defined by the sand mold and core. After sufficient cooling time, the molding boxes are opened. The sand mold is broken apart to reveal the rough cast impellers. Excess material from the gating system, including runners and risers, is cut away. The castings are then cleaned to remove any remaining sand and surface residue. Finally, the impellers undergo finishing operations such as grinding and precision machining to achieve the required dimensional tolerances and smooth blade surfaces. These finishing steps ensure proper balance and hydraulic efficiency, completing the manufacturing process of the pump impeller. The manufacturing process of large shell and tube heat exchangers begins with stainless steel plates prepared for forming the main shell. Each stainless steel plate is carefully rolled into a cylindrical shape to create the shell section. After rolling, the longitudinal seams are welded, and multiple shell sections are precisely aligned and joined together to achieve the required overall length. While the shell fabrication is in progress, the internal support structure, known as the baffle cage, is assembled on the workshop floor. The baffles are positioned and fixed within supporting rods to form a rigid cage that will later guide the flow of fluid across the tube bundle. At the same time, expansion bellows are point welded to the shell to compensate for thermal expansion during operation. Once these components are installed, the completed shell section measures approximately 7 meters in length. To meet the promised delivery date, production continues around the clock. As the baffle cage reaches completion, it is carefully lifted and inserted into the shell. This step requires accurate alignment to ensure proper positioning inside the cylindrical body. Next, the tube bundle assembly begins. The first tubes are inserted one by one through the baffles and into the first tube plate. At this stage, only the first tube plate is fully welded to the shell. After positioning the second tube plate at the opposite end, the remaining tubes are inserted until the entire bundle is complete. When all tubes are in place, they are point welded to secure them to the tube plates. With the tubes fixed, orbital welding and roller expansion operations can begin. Two operators start the orbital welding process, welding the tubes to the tube plates in a zigzag pattern. This sequence is carefully followed to prevent uneven stress and distortion on the tube plate. After welding, each tube undergoes roller expansion to ensure a tight and reliable mechanical fit between the tubes and the tube plates. Once fabrication is complete, the entire unit is subjected to a pressure test to verify its structural integrity and leak tightness. After successful testing, the heat exchanger is prepared for transportation. Specially manufactured saddles are installed to support the heavy unit securely on the truck. Finally, using a 16-ton lift, the exchanger is loaded for delivery. The manufacturing process is now complete, and the large shell and tube heat exchanger is ready for installation and operation. The extrusion process begins with solid aluminum logs or billets, typically alloys 6463 and 6061. Each billet is first placed into a preheating oven, where it is heated to approximately 900 degrees Fahrenheit. At this temperature, the aluminum reaches a plastic state. It becomes soft and malleable under extreme pressure but does not melt. Once heated, the billet exits the oven and is sheared into an extrudable length, usually about 30 inches, depending on the profile design. The hot billet is then transferred by an extrusion loader into the press container. A powerful hydraulic ram applies up to 3,000 tons of pressure, forcing the aluminum through a precision steel extrusion die. As the heated metal flows through the die opening, it takes on the exact cross-sectional shape of the die and emerges as a continuous length of formed aluminum profile. Throughout this stage, the entire process is monitored by digital readouts, and all production data is stored to develop optimized extrusion recipes for each specific profile. As the 900 degrees Fahrenheit extrusion exits the press, an automated puller grips the leading end and guides it along a 150-foot runout table. This prevents twisting or surface contact between profiles. A series of cooling fans reduces the temperature to room level. At this point, the aluminum is in a soft T4 temper condition. Alternative cooling methods, such as water quenching, may also be applied when higher strength tempers are required. The continuous extrusion is cut to length using a movable hot saw. The separated sections are transferred to a cooling table, where natural shrinkage and distortion may occur. To correct this, each profile is stretched approximately 3% of its total length, restoring straightness and dimensional accuracy within specified tolerances. Next, a finish saw cuts the straightened extrusions into final stock lengths of 20 feet or less. The parts are then loaded onto aging racks and placed in an artificial aging oven to achieve harder tempers such as T5 or T6. The extrusion dies, manufactured from H13 tool steel, vary in size and may contain multiple profile openings, enabling the production of thousands of custom-designed aluminum shapes. The HDPE double-wall corrugated pipe extrusion line is a high-performance production system designed to manufacture durable pipes with a corrugated outer wall and a smooth inner layer. Using dual single-screw extruders, the line simultaneously processes the inner and outer layers, allowing different materials or colors. A co-extrusion die head ensures uniform wall thickness, while the corrugator shapes the outer profile using vacuum or pressure forming. Controlled by a PLC system, the line delivers precise, automated operation for producing pipes used in drainage, sewerage, and underground cable protection. The Soralus FR8000 floor-type milling and boring machine, developed by Soralus, is a high-performance solution designed for machining large and heavy components with maximum precision and flexibility. This machine integrates advanced automation systems and a robust structural design to meet demanding industrial applications. One of its key features is the robot tool changer, equipped with a tool magazine capable of storing up to 130 tools. This large capacity allows continuous machining operations with minimal downtime for manual tool replacement. In addition, the automatic head-changing system enables fast and precise exchange of different milling heads, increasing productivity and expanding machining capabilities. The machine is fitted with a stepless universal head, which provides continuous angular positioning for complex multi-face machining. A horizontal head with a diameter of 230 mm and a length of 480 mm ensures powerful cutting performance, especially in heavy-duty boring and milling operations. The external head refrigeration system effectively controls temperature during operation, maintaining dimensional accuracy and extending tool life. The rotary traveling table measures 3,500 by 3,000 mm, with a width of 2,500 mm and a load capacity of up to 60 tons. This heavy-duty table allows the machining of oversized workpieces while ensuring stability and precision. Furthermore, the traveling operator platform enhances accessibility and safety, enabling the operator to monitor large-scale machining processes efficiently. Overall, the Sorolus FR8000 represents a reliable and versatile floor-type milling and boring solution for heavy industry. The company known today as Kamahara Chukojo Company, Limited, was founded in 1955 in Kochi City under the name Kochi Tokushu Steel. In its early years, the factory mainly produced cast steel components for harbor cranes and industrial machinery. As Japan's shipbuilding industry expanded, the company changed its name in 1966 and steadily enlarged its facilities. With continuous investment in modern electric furnaces and advanced machinery, it has grown into the only foundry in Shikoku capable of manufacturing castings in the 40-ton class. Today, it stands among the top 10 domestic manufacturers of marine cast steel products, earning trust through consistent quality and reliability. The company specializes in heavy-duty cast steel components for ships, where strength and durability are critical. Its products are used in tankers, large ferries, and even naval escort vessels operated by the Japan Self-Defense Forces. Many of these components are installed around the propeller system, an area subjected to tremendous stress and harsh marine conditions. One example is the rudder horn, a massive structural casting that supports the rudder and can weigh up to 4 tons. Another key product is the propeller boss, a large hub through which the propeller shaft passes, weighing as much as 17 tons. The company also produces stator fins, smaller but highly functional components that optimize water flow from the propeller toward the rudder, contributing to improved fuel efficiency. The manufacturing process begins with mold preparation. Cast steel products are created by pouring molten steel into specially prepared molds. Depending on the size and complexity of the component, wooden patterns are first produced with precise dimensions. These patterns are carefully placed inside large molding frames using overhead cranes. The space between the frame and the pattern is filled with specially blended sand containing hardening agents to ensure strength and dimensional stability. A refractory coating is applied to prevent burning and improve surface quality. The mold halves are then assembled and securely fixed, completing the mold setup. Melting is carried out in a large electric furnace. Scrap steel and raw materials are heated for approximately 4 hours until the temperature reaches around 1600 degrees Celsius. During this process, alloying elements such as manganese and silicon are added to adjust the chemical composition according to strict material specifications. Impurities are carefully removed to guarantee the required mechanical properties. Once ready, the molten steel called melt or molten metal is tapped into a massive ladle. The sight of the glowing liquid steel flowing into the ladle is striking, resembling a bright, fluid stream of light. The ladle is transported by crane to the prepared mold. Positioning is carried out with precision, and the molten steel is poured steadily yet swiftly into the cavity. This moment demands coordination and experience, as proper filling determines the internal soundness of the casting. After pouring, the casting is left to cool and solidify for several days, depending on its size and thickness. Once solidified, the mold is broken away and the rough casting is revealed. Excess material is cut off, and welding may be performed to refine the shape. Comprehensive inspections follow, including dimensional checks, mechanical property testing for strength and toughness, and non-destructive examinations conducted from various angles to detect internal defects. Finally, finishing operations are performed. Grinding improves the surface, and large machining centers carry out precise mechanical processing to meet exact tolerances. The completed cast steel products are then shipped to shipyards, where they become critical components of large vessels. Through decades of technological advancement and strict quality control, Kamihara Chukojo continues to support the maritime industry with reliable, high-strength cast steel solutions. Founded in 1962, Fundição Moreno has continuously combined quality and technology to support the expansion of Brazil's sugar and ethanol industry. Strategically located in Sertãozinho, in the state of São Paulo, within the Ribeirão Preto region, widely recognized as the Brazilian capital of agribusiness. The company benefits from a competitive position in this demanding market segment. Moreno is equipped to manufacture cast steel and cast iron components with up to 30 tons of molten metal, supplying parts in as-cast, rough machined, or fully machined conditions. The industrial complex covers 70,000 square meters, including 25,000 square meters of built area. Within this structure, and supported by a long-standing tradition of excellence, Moreno took a decisive step forward in 2006 by launching its own line of milling equipment designed for sugar mills. The Moreno mills are produced according to the strictest quality standards that have characterized the company since its foundation. The foundry has been recognized with the ABMC/Sindimac Award for Best Foundry Company and achieved ISO 9002 certification in March 2000. Skilled professionals, creative engineering, precision, and advanced technology transform raw metal into essential components such as housings, shells, rollers, bearings, trash plates, and other parts that together form nearly 230 tons of milling equipment. Each project begins with significant investment in pattern development, as model accuracy is crucial to achieving the required casting quality. Throughout the plant, commitment is evident in molding, pouring, heat treatment, finishing, machining, and pre-assembly operations. Quality assurance is reinforced by laboratory testing, including tensile analysis, chemical composition verification using state-of-the-art spectrometers, magnetic particle inspection, ultrasonic and dye penetrant testing, dimensional control, and impact testing. With professionalism, modern technology, and confidence in the future, Moreno's milling units, first presented at Finisucro 2006, demonstrate its ongoing commitment to strengthening the productivity and profitability of Brazil's sugar energy sector. Kingston Technology, headquartered in Fountain Valley, specializes in the design and manufacture of computer memory and flash-based storage products, including solid-state drives, USB flash drives, flash cards, and embedded flash chips for mobile phones and tablets. With more than 2,000 products and a compatibility database supporting over 41,000 devices, the company serves platforms ranging from mobile systems to enterprise servers. Every product begins in the engineering department, where teams develop new technologies and refine existing ones. After design completion, prototypes are delivered to compatibility labs for real-world testing on specific motherboards and systems. When next-generation platforms are not yet available, advanced proprietary testers simulate future system parameters using software developed by Kingston's engineers. These platforms also qualify critical components such as DRAM, NAND, controllers, registers, and passive devices. Kingston operates more than 64 manufacturing lines worldwide and has the capacity to produce over 300 million units annually. Raw materials, including DRAM components, are sourced from leading semiconductor suppliers. Assembly takes place on surface mount technology lines, beginning with solder paste printing onto printed circuit boards. Automated optical inspection verifies solder accuracy before mounting machines place passive components and DRAM chips. The boards then pass through a reflow oven with a 7-stage temperature profile reaching 500 degrees Fahrenheit to cure the solder, followed by final inspection and depaneling using computer-controlled router saws. Production testing is a defining strength. Patented systems, such as the KT2100 and KT2500, enable high-volume automated memory testing. Server-grade modules undergo burn-in testing in KT2400 chambers at 212 degrees Fahrenheit, simulating extreme operating conditions. Even a single defective cell disqualifies a module, ensuring Kingston maintains exceptionally high-quality standards across billions of memory cells. The generator is first secured inside the workshop, and access covers are removed to expose the rotor and stator assembly. Before lifting begins, technicians carefully measure the radial clearance, which allows only a narrow tolerance of approximately 3/4 inch. The 20-foot-long rotor, weighing over 45,000 pounds, must be extracted with extreme precision to avoid contact with the stator core. A custom 20-foot steel tube with a 1-inch wall thickness weighing about 300 pounds is prepared as the primary support beam. Two 50-ton cranes are positioned above the generator to share the load evenly. The lifting system is aligned precisely with the rotor shaft centerline. Rigging components are attached, and the cranes gradually take the rotor's weight until it is fully supported and balanced. Using a hydraulically actuated rotor removal system, controlled pushing and pulling forces are applied to initiate axial movement. The rotor is slowly floated out of the stator bore, maintaining constant height control and alignment throughout the 20-foot extraction path. Operators continuously monitor clearances and crane synchronization. Once fully removed, the rotor is transferred safely onto designated supports for inspection and repair. The process begins with flat steel sheets being fed into a hydraulic press fitted with a precision-forming die. The sheet is accurately positioned beneath the die to ensure consistent alignment before each pressing cycle. When the press descends, the first action is blanking. The die cuts the steel into the required outline, separating the workpiece from excess scrap material. This blanking operation establishes the external contour of one magazine half with controlled dimensional accuracy. Immediately following blanking, the forming stage takes place within the same press system. The flat blank is shaped into a curved profile that matches the required tapered geometry. The die gradually bends the steel under high pressure, ensuring uniform curvature from top to bottom. During this forming cycle, reinforcing ribs are also stamped into the sidewalls. These longitudinal ribs are pressed directly into the surface of the metal. Their function is to improve rigidity and structural strength without increasing material thickness or overall weight. Integrating the ribs into the stamping process eliminates the need for additional reinforcement components. After forming, the stamped half is removed and transferred to a trimming station. At this stage, any excess metal along the edges is cut away to achieve clean, precise contours. Burrs generated during blanking are carefully removed to produce smooth mating surfaces. Accurate trimming is essential because uneven edges would interfere with proper alignment during assembly. Each half is inspected to verify curvature, rib definition, and dimensional consistency. The stamping and trimming sequence is repeated to produce a matching second half. Once both curved shells are completed and approved, they proceed to assembly. The two halves are carefully positioned together so that their front and rear edges align precisely. Special fixtures hold them securely in place to maintain symmetry and prevent movement. At this stage, the aligned shells form the complete outer body, prepared for permanent joining along the seams. With the two halves clamped firmly in alignment, welding is carried out along the front and rear seams. In spot welding, electrodes press against the steel surfaces and deliver controlled bursts of electrical current. The localized heat fuses the sheets together at evenly spaced points, creating strong joints while minimizing distortion. Each weld location is carefully positioned to ensure uniform strength along the entire seam. In some cases, basic manual welding is performed instead. The operator runs a continuous weld bead along the seam to permanently bond the halves. After welding, the joints are inspected for penetration, uniformity, and structural integrity. Any irregularities are corrected, and excess weld material is smoothed to maintain a clean exterior finish. The welded body is thoroughly cleaned to remove oil, scale, and residue before finishing. It is then treated with either bluing or black phosphate coating to create a protective anti-corrosion layer. After drying and final inspection, the completed steel magazine body proceeds to subsequent assembly stages. The production of stainless steel spoons begins in the raw material preparation workshop, where stainless steel sheets are received and inspected. The initial material is selected according to the required thickness and grade. At the same time, the molds used for shaping and stamping are processed in the tooling department to ensure accurate dimensions and smooth forming during later stages. After preparation, the stainless steel sheets are fed into a stamping and shearing process. Large presses cut the sheets into rough spoon-shaped blanks. These blanks then undergo rolling, where the material is pressed and elongated to achieve the required thickness and uniform structure. After rolling, the surface becomes smoother and more consistent. Trimming is performed next to remove excess material along the edges, creating a cleaner outline and improving the overall edge quality. The trimmed blanks proceed to the forming stage. Through pressing and forming operations, the bowl of the spoon is shaped, and the handle is gradually curved to its final contour. If the spoon design requires a separate head and handle, the head welding process is carried out at this stage. The spoon bowl is welded securely to the handle, ensuring structural strength. After welding, side grinding is performed to smooth the welded areas and refine the edges. Following forming and welding, the spoons move to the polishing and grinding section. First, mechanical polishing removes surface scratches and marks left by stamping and forming. Automatic polishing machines then provide a consistent surface finish across large batches. After automated treatment, workers carry out manual polishing to enhance gloss and eliminate any remaining imperfections, especially in detailed or curved areas. Once polishing is complete, the products are thoroughly cleaned to remove polishing compounds, metal dust, and residues. The cleaning process ensures that each spoon meets hygiene standards and has a bright stainless surface. Next, laser engraving is performed if branding or decorative patterns are required. High-precision laser equipment marks logos or designs onto the handle without damaging the polished surface. After engraving, the spoons undergo strict quality inspection. Inspectors check dimensions, surface finish, weld strength, and overall appearance. Only products that meet the standards proceed to packaging. Finally, the spoons are packed carefully to prevent scratches or deformation during transportation, completing the stainless steel spoon manufacturing process.